Ladies and gentlemen, this is a phenomenon that I have observed for all the years I've been teaching. The day after the midterm, people decide not to come to class. I don't know why that is. You're not because you guys are here, but your colleagues who aren't here are not the first people to behave that way. It's the way people always behave. I'm not quite sure why, since the day after the midterm is when the next thing gets introduced, and if you miss the introduction to the next thing, you've missed something. But whatever, you're all here, I'm glad, and we'll go about what we need to go about. First thing is the midterm. The results were about what they usually are, which is good. Scores were generally high. The mean out of 60 was about 53.5. It's not an absolutely precise score because a couple of the sections haven't been recorded yet, but it'll be right about that. So let me say just a couple of things. Thing number one is, if you scored 55 or higher, that's great. Don't sweat figure out why you didn't get those couple of points, but don't feel as though you're somehow prevented from getting as high a score or high a grade as you want because you happen to miss a point or two here or there. If you scored lower than that, especially if you scored below 50, 45, something like that, you might want to think about the way you've been going about your work. And there were a bunch of suggestions in the message that I sent out the other day, so I won't go over them all now, but if you haven't been sort of seriously taking the quizzes every week, if you haven't actually tried to do the preparation parts of the homework, if you have been letting your partner carry the ball in the lab, all of those are not ideal strategies. And the whole reason that we have a midterm in the fourth week is so that people who need to change the way they're working get some indication of that in time for them to make those changes. So nobody's grade is doomed, but if you don't know why you got the low score you got, figure out how to answer the questions, but figure out what changes you need to make in the way you're working. So are there comments or questions about that before we go on to the next story? Okay. Then, the first thing on the agenda today is to talk about mutability and immutability and parameter passing some more. And the reason we care about these things, the reason why this comes up as an issue is for efficiency, right? So programs have to have a lot of qualities. They have to be correct. If they don't produce the correct answers, nothing else matters. It doesn't matter how fast you produce the wrong answers. It doesn't actually matter how good the user interface is if the answers are wrong. So correctness is absolutely the first thing. If you don't have the right answers, nothing else matters. But once you have the right answers, or while you're designing to produce the right answers, you also need to design to be efficient for you as the developer and for your successor developers and the other members of your team. So there's human efficiency. Okay, so one kind of efficiency is human efficiency, and all the things we've talked about a bunch of times already. There was even a question about it on the exam, to make the software development process produce correct results and not take too long and not introduce bugs and that sort of thing. That's one aspect of human efficiency that we care about. Another aspect of human efficiency is for the end user of the program. right? If you have a program that lots of people are using and your program has the buttons too close together, so people push the wrong button a lot of times and have to go back. Well, if a lot of people use that program, you're wasting a lot of their collective time. And these days, it's human efficiency that's really the most important thing. If you were to go back in time 50 years, let's say, a university this size would have had one computer. Let me think about this. 50 years. That's okay. A university this size would have had one computer. It would have had less power than the chip in my NerdWatch here, and everybody would sign up for a half-hour block of time once every 2 weeks on the computer, and they'd be glad to get it. Well, in a situation like that, right, where you have to sign up for a half-hour block and then you go back to your office for 2 weeks to plan for your next half-hour block, it's the computer's time that's the most valuable. And they kept it going 24 hours a day, and the less important people had their half-hour block of time at 2 in the morning, and the more important people had it during daylight. But in that circumstance 50 years ago, it was the computer whose time, so to speak, was most important. Switch to today, right? Half the people in this very room have computers on their desks right in front of them that have many, many, many times the power of those 50-year-old university computers. And most of the time, I mean, if you're not checking eBay or playing World of Warcraft or doing some other thing, most of the time it's sitting here not doing anything. And those of you who don't have your computers here in front of you today have them at home, and probably they're not doing anything most of the day either. There are these sort of run-in-the-background programs that collectively solve big problems, and that's another story. But most of the time, your computers, thousands of times more powerful than the computers 50 years ago, sit idle. And today, that makes economic sense, because your time is more valuable than, more expensive than the computer's time. Right? I mean, you can look at it this way. The computer from 50 years ago cost many, many, many times a person's annual salary. Your computers here, right, cost a small fraction of a typical person's annual salary. Right? So the computer can do a whole lot more, but it's a less precious resource than it was, and it makes perfect economic sense for everybody to have this powerful machine that most of the time they don't use, just so that when they need it, it's there for you right at the moment. You don't have to wait 2 weeks. You don't have to sign up for a block of time. It's right there. If you think about it, you have maybe your laptop, and maybe you have some kind of computational device like this, and maybe you have something that's intermediately sized between this and that, and that all makes sense. So today, moral of the story, people time is more expensive than computer time. Right? Doesn't mean we have to think. Doesn't mean we don't have to think about computer time and computer efficiency. That's going to be the next line on the slide, but people time is important, and so the human efficiency for the end user of the program is another thing that in the design of software you need to think about. So we in this class are thinking a little bit about the human efficiency for the programmer. We're not thinking very much about the human efficiency for the end user. Every so often we'll mention something. But then, after we talk about the human efficiency, we have the machine efficiency, which comes in a bunch of categories. There's processor time, there's a lot of computational resources that your computer has to give you. There's the time for the processor, right, the actual execution of instructions, but there's how much memory you have, and there's how much disk you have, there's how much network traffic you need to use, and there's how much power you need to use. That's important on many kinds of devices. And balancing those out, somehow somebody's got to be thinking about. That is also not something we spend a lot of time worrying about in the first programming course. Right? By next quarter, certainly by third quarter, there will be more consideration of efficiency. But mostly we don't have to think too much about that. We learn common patterns for handling common situations that produce the right results, and we're mostly pretty happy. And that's an appropriate set of things to be concerned about in a first course. But the tools we use, in our case, Python as a programming language, wasn't designed for students in a first programming course. Right? If you talk to Guido van Rossum, he says, well, I'm very pleased that people are teaching introductory programming with Python, but that was never my idea. I'm not a teacher. I'm a programmer, and I designed Python to solve conveniently a whole class of programs of the sort that I typically work on. And so when Guido van Rossum made his design decisions about Python, some of them were based on the machine efficiency of doing things, because real professional programmers have to think about that. And so because he didn't try to design the language to hide those things from us, sometimes we trip over them. And this mutability, immutability issue is one of the things that we trip over, because Guido tried to design Python to make what he felt were intelligent decisions about efficiency, about how things happen under the hood so that they don't take up too much processor time, memory space, blah, blah, blah. And sometimes the results of those decisions look a little strange to us. And so we're going to talk about some of those decisions today, a couple of them, and see what they are and be aware of them, because we have to be aware of them, right? Our alternative, in general, Python, compared, for example, to other popular programming languages, Python's pretty good for teaching introductory programming. There's a lot of stuff that we don't have to think about in Python from the first day of the course that aren't necessary, where, in, say, Java or C++, which have their advantages too, but they force you to think about more stuff from the very beginning. That isn't really important to a basic understanding of programming. So, Python is a good choice. There are programming languages that were designed as teaching languages, right? That weren't particularly designed for writing large-scale programs, and that don't pay so much attention to these practical efficiency issues. And it's not a terrible decision to use a language like that in a first course, but students tend not to like it. Right? They tend to like to learn a language that they've heard of and that people use in industry somewhere. And so, one of the reasons we made the decision for Python instead of for, something else that was more exclusively teaching-oriented is because, Python's out there and it's practical and it, people use it. So that's why we have to spend the next half hour or 45 minutes talking about mutability and immutability and passing parameters by reference and passing parameters by value, why we have to look under the hood to see what's going on. It's because some of these efficiency decisions that Guido van Rossum made when he designed Python to be a practical programming language for practical programmers, some of those decisions we have to be aware of, or our programs are going to behave in ways that just seem weird. So, that's the story. Let's see how to do this here. Okay, mutable means changeable. Changeable in our context, in place. Right? So every value we store is stored somewhere in memory. There's a box in memory into which that value goes. Can you put a new value in that box? Or do you have to create a new value somewhere else and assign a name to that new value somewhere else? That's the kind of mutability, immutability question. Right, and you've seen the results of this because we can change, L sub 3, lists are mutable, we can change an individual element of a list without recopying the whole list. We can't change the price field of some name tuple right there in place, we have to create a new name tuple, maybe with all the old values and the new price, or using the underscore replace method. Either way, creates a new name tuple, which we can then assign the name to, right? The variable name we can, what the variable points to can change, but the value itself, we can't plug a new value in. So that's what's happening. You've sort of seen that. Another example of mutation, changing in place versus non-mutation, is there's been the sort method, which changes the list in place, and the sorted function, which takes a list and gives you another copy of the list changed into order, which you can then print out or assign or do what you need to do. So there is this page on the course resources sheet. Okay, I flashed this up once before, but there we go. But that's a kind of summary of the data structures we're going to learn this quarter. And there's a column that says mutable, immutable, so you can remember if you forget. But what I want to do today to start is to show you how some of these things work. With a tool called pythontutor.com. So, you can use this, right? pythontutor.com, there it is. And there we go. We want to be sure we're using Python 3. Doesn't matter, 3.3, 3.4 doesn't matter for us, but not 2.7, right? Things don't work quite the same way. Weird stuff will happen, and it won't be clear why. So Python 3.3 is what we want. And let's just see what happens. So okay, so so here's some Python, right? We have a list, we have a name, we set the second element of the list to a different value. We'll print the list out. Let's print the list out to begin with. We don't really need the print statements because the whole point of Python Tutor is that it shows us what's happening under the hood. So down here, almost at the very bottom, maybe I can make it show up, is the Visualize Execution button. So we do that. And now we have our code with a little pointer that tells us which line we're executing. And we can step through it step by step, one step forward, right? Here are the variables that we have. There's a variable called original, and it refers to this 4-element list, numbered 0, 1, 2, 3, 23, 45, 67, 89. Okay? So next instruction prints the value of that, which is what we'd expect. Next instruction says name and sets that to Donald Duck. You can kind of see the difference, right? One of the ways of seeing what things are mutable and what things are immutable is that the immutable things are shown here in the what we call the global frame in the set of variables that we have in our program. Here we just have something that points to the data stored out somewhere else. I mean, the place these things are stored is called the heap, but it's a different part of memory, and it's, well, we'll see what happens. So I can do the next instruction. Original sub 2 gets 999. You see that? It just happened. We can back up. Right? Here it was before. do line number 4, look at this, watch it change. Boom, we stick 999 in there. Lists are mutable. We just mutated the list, okay? And so we change the list, we can print it out, and there's the changed value, and everything's changed. Now, what happens if I edit the code and I say name sub 2 gets x? Let me So, putting print statements in, as I say, isn't really necessary in Python tutor, so we can see what happens in memory, right? And the whole reason we're doing this is to see what's going on. But if you're working in idle and you want to see what's happening in your code, and for some reason you don't want to fire up pythontutor.com, which you should do if you need it because it's there and it's free and it's a good tool. But if you don't want to do it, you can get a view of what's happening, snapshots of what's happening, by putting in print statements. That's also a debugging technique, right? If your program isn't producing the right results, but isn't producing an error message, right? You've got to figure out where your program's going off track. And going off track means somehow some variable somewhere has the wrong value. Well, at some point in your code, your variable was assigned the wrong value. You have to figure out where that is. So you print it out at the top, print it out at the bottom, print it out in the middle, and now if the value in the middle is what you expect it to be in the middle, then the first half of your code probably didn't introduce the error, and the error is probably in the second half of your code, which you can divide up further. But just kind of corralling the error by surrounding it with print statements, that's probably the simplest debugging technique. So, whoops, I don't want that. All right, so here we go. This is the same, and there's Donald Duck. We'll print Donald Duck, say name sub 2 gets x, blammo. String object does not support item assignment, right? We're trying to assign into the middle of the string. We can't do that because strings are immutable, and there's the error message that says that, so we're out of luck. Okay, so that's not going to do it. So let's see how else we could accomplish the same thing. So this one is no good. This way would work. Right? Use cross sections, use slices. So first 3 characters, 0, 1, and 2, and then, well, 0 to 2 gives us 0 and 1, actually. And then the x, and then character 3 through the n, stick those all together. This would work fine. So there's Donald Duck. We print it out. Now you see it? There's Donald Duck. We do this statement, stick the x in there, and now we can print it, and we have the x, and we keep on going. Okay. So, we can do it. We can do it that way. Of course, we can do it. Quote do capital X ALD space DUCK. Right. We just assign it a new string. That would be even more straightforward. All right. So, we could do it. Here's even another way to do it, in fact. Whoops. We could say right? Just build up the result. Right, so go, position number I from 0 to the length of the name minus 1. If this is the character we want to change, we say stick an X onto it. Otherwise, say stick that character on. Right, so we go through character by character by character by character. If it's the one we want, plug the X in. If it's not, plug in the character from the original. And this works just the same in the end as everything else. We can see there's Donald Duck. There's our result. So far, it's empty. I starts at 0. Is I 2? No. So we do the else part and tack on to the result the first character, character sub 0 of the name. And there's the D. And now I gets 2, or I gets 1, I mean, second item. And it's not equal to 2, so we tack on name sub 1. And then I gets 2. There it is. I is equal to 2, so we stick on an X instead and not the name. And we keep on going. I is 10, 10th character. Are we at the end of the length of the name? Yes, we are. So we go on to the next thing. We print out the name. The sad thing about pythontutor.com is you wish for a mile-wide screen, right? For a program of any size, the code and the output and the visualizations just don't all fit on one thing, and you've got to move around a little bit. But there's... okay. So what did we get? We got Donald Duck again. Why did I get that? I printed the name again, right? I mean, I have the name. The name's Donald Duck. I created this thing called result, which has the right result, but what I printed out was the name, if I were to print out the result, I'd get the result. And this time, instead of stepping through, I'm just going to go through lightning speed. There it is. We're done. Now we have the name again at the end. And the name wasn't changed, right? We didn't do anything here to change the name. We just built up a new result, which we printed out and got what we wanted. And everything else is the same. Okay? So comments or questions about any of this so far? Yeah.
When you declare a variable called result, is there any other way to declare it other than just?
Yeah, so in Python, we don't have to declare variables. That is, we don't have to say up front, hey, I'm going to use the variable x, and it's going to be like this, except in parameters. Right? So in a function definition, we do give the name of the parameter in the def line, in the function header line. But that's the only place in Python. If we want to use some other variable just in our code, we just type the name, and assuming Python's never seen it before, it says, OK, new variable. And we saw it in the blue block there. We came upon a new variable name, and we just got the new line in the blue block. Python reserved some memory for us, and now it's there for us to do what we want to do. Okay, good. Other, yeah.
Why is it like stuff like Python 2, like why isn't it in the actual I/O program? Why is it we have to access online rather than be on the actual program?
Well, because the guy who developed this is different from Guido van Rossum and the Python project. I mean, there's no reason, there's no theoretical reason why this visualization couldn't be incorporated into IDLE. Right? There are other, well, actually, I don't know if there are other, I guess there are other IDEs that give you a little more visualization. As far as I know, this is the sort of the best visualization tool. And the guy who wrote this, a guy named Philip Guo, and he used to work at Google. I'm not sure if he still does or not. But But this was an independent project is why. It started out separate from the Python project. He said, I want to build a visualization tool, and I'm going to make it web accessible, and he did that. And, in a way that was easier for him because he didn't have to coordinate with the Python people. He just built his tool. And so that's the stage of evolution where we are right now. There's no fundamental reason why the Python project couldn't say, hey, Philip, how about letting us incorporate this in idle? But as far as I know, they haven't done that or something. Yeah, good. Yeah.
Would it work if instead of making the result vector, you just said for I range of the length, if I equals 2, then names of I would equal x, and for everything else, I equals names of I?
Yeah, good question. But we can't say name sub I is assigned something because we know that strings are immutable. We can't assign into the inside of a string. Okay? So, sorry to say we can't do it that way. Yeah. Uh-huh.
In the lab, I was getting errors that said type whatever, like result is not defined, and then I declared something, I set it equals to value, and then that would fix the error.
Well, it gives it a type, if that's your question. So, once if we've never mentioned the name, right, if we just say, what's the type of banana, it's going to say, I don't know what banana is. I've never seen it before. If we say banana gets 17, and we say, what's the type of banana? Well, now banana has a value. It's 17, and we can say, yeah, that's an int. Okay, good. Other comments or questions so far? Okay. So far so good. Let me, don't want all this. Let me take this code and copy it over to our notes. And let me make this point. When we pass right, when we call a function right with an argument that becomes a parameter, two things can happen. All right, let's see what I'm talking about here. Let's keep original and name, and let's define a function. Actually, double, interestingly enough, will work for both the string and the list, and a number, I mean. No, not what I want to do. Let's try it this way. Okay, so we're going to take a we're going to take a list of something and an item of that type, and we're going to add that thing to the end of the list. Now, we have the extend method and the append method and so on, which we'll talk about as we go through here, but let's write a function that has that result, first of all. So All right, so let's just say L dot append I. Okay, so this, right, this is a method on L, so it changes this has a side effect, and we're done. So we can say all right, so we have our list. We're going to call add to end. We expect add to end to do two things, and we'll see why in a second, but we expect it to return the list L. So we're going to get a list here with 999 added to the end. But this is also going to change L, and we'll see the link and why that happens in a second. So when we print this out, this is going to be changed. We're going to have the 999 at the end, and that's an example of a side effect. So, in general, we want to do one thing or the other. Right? In general, we either want to have the side effect change something in the outside world and not return anything, or we want to return something and not have any other change in the outside world. And the latter, if you have a choice, is better, so that all of the movement happens with what you pass into a function or what you return, and it makes it easier to reason about your program, to be, convince yourself that it works, to find bugs if there are bugs. If everything that your program does pretty much is based on what you pass into a function and what you return from a function, it's harder to trace those things if any statement in the function can change something in the outside world. But it does sometimes, and that's what we're here to talk about. So let's watch this happen. So here's our original. There's Donald Duck. We've just defined the function, right? So add to end is this function that takes a list and an item. We can print the original. We can print add to end of the original. So we call add to end. Right here we're calling it now. A new little environment comes up where, and this is what I typed in the notes a second ago, the parameter L refers back to this original list in memory. Okay? The alternative would have been to have a copy of the list. Well, it wouldn't be actually in this box, but it would be out here, another copy of the list. And we'll see an example of making that happen in a second. Okay? So the alternative would be to have a copy of L that's exclusively for the use of the function. When the function goes away, it cleans itself up, and we're left with the original untouched. That would be the alternative. That's not what's happening here, because every time we talk about L, we're talking about this same list object. Now, why is that? It's because it costs something to make a copy. And if you have a list, right, a list in your program, probably in a real program, probably isn't going to have 4 elements. It's probably going to have 40,000 elements. Right? And copying all 40,000 elements to use it in a function, that takes time. So that's Guido's judgment, right? Guido's judgment is, not unreasonable, that when you pass a list to a function, when you pass any mutable type to a function, you pass a reference to it, that arrow, that pointer, you pass a reference to it so that you're actually talking about the same object that you had in the argument list, namely our list called original. So anything we do to L in the function is going to happen to the list original, because they're both pointing to the same thing. There's 2 names for the same thing. Why? To avoid having to copy that 40,000 element list, which takes a long time. Strings, Guido judged, weren't typically so long. right? Now, maybe that's the wrong judgment, right? And certainly you can think of applications where you have, million character strings and whatever, but we'll see this when we do this same thing with a string. The string just gets copied, right? And if we had a parameter that's a string and pass a string in, and there would be another copy of the string in the blue box, right? And Guido's judgment that strings aren't so big, so copying them as the normal activity doesn't cost so much. Same thing with name tuples. Right? So, a name tuple, however many fields it has, is probably not going to have 40,000 fields. Now, the name tuple could contain a list with 40,000 fields, right? You have a restaurant which has a list of dishes, and I don't know, 40,000 dishes on a menu is a lot, but maybe you have a couple hundred in certain kinds of restaurants. And the list is still going to be, yellow out there on the heap, not copied. But the structure of the name tuple, name, cuisine, phone, list of dishes, whatever, that would be copied because that itself isn't so big. So why are we here talking about this? Because the language was designed to make some decisions based on how likely it is that copying the whole parameter is going to cost us a lot because the parameter is really big. Says lists could be really big. Dictionaries, which we'll learn eventually, could be really big, and so we're not going to make a copy. At least we're not going to make a copy automatically. Automatically, we'll just refer back to the original object, and changes here will be reflected even when the function goes away. So let's watch it happen. Right? So we're right here ready to execute the function from this function call. So we've passed in the parameters. Here's L, the list that points to original. Here's 999. Right? Ints are immutable. Right? You can't change the middle digit of the number, so it stays. It has just a copy here, and so L dot append the number. There it is, right? Back up again, forward again. We append to the same thing because both the parameter L and original are referring to the same parts in memory, the same object in memory. And so now we're ready to return, right? So what's the value of L? It's the reference to this location in memory, and so the return value is L, which is the reference to this location in memory. So we return that reference, and we printed that out. Here it is. Right? So we have the reference to L. That was the value of the function call, and so we printed it out. There it is. But when we say print the original's been changed too. So there we go. Okay? So that's the normal thing that happens. Right? And Guido is, at least to his mind, doing us a favor by not forcing us to copy our potentially huge list and just using the original in place. Okay? So, fair enough. Okay, comments or questions about this so far? All right, so let's see a variant of this. Let's edit the code. And let's leave this out. We just saw how that works. But let's say okay, let's have a new local variable, and let's say let's set that to the whole list. Now, if we were to say, actually, let me do an intermediate step first. Okay, so all right, so I passed in the list. We had a reference to it. If I have a separate variable here and assigned to L, it's just going to be another link back to the original copy. And so, so returning, how do I want to do this? Doing this is going to make the same change that we made before. So let's watch it happen. There's our function we call with parameter L, right? Same, L is original, 999 is the parameter, right? We're ready to start executing the function. Result gets L, right? L is a reference back to the same original plot of land in memory. So result likewise returns, and we can append to it. We can print that out. We can't quite see it, but there's the return value. Print it out, print the original, it got changed. So the same thing happened here, just using another variable name didn't help us. But now let's look at a relatively slight variation. If we were just to say, not this, but, well, here it is actually. So I don't need this line here, it's the same thing. If I say not L, which is just the reference back to the original list, but if I say L from beginning to end, this kind of cross-section with nothing on either side of the colon, that's just a way of saying the whole list from 0 to length minus 1. That makes a copy. Why? Well, that's just how Python works. This gives us a new copy of the list. We'll see that in a minute. So we're going to append to the result. We'll return the result, which will be the new list. So we'll get this line to print it out with the extra 999, but the original won't be changed. Okay, so let's do it. Okay, so we call the function with original and 999. So we start out with L pointing to the original, right? That's what happens when we pass the parameter. But now we say set result to a copy of the list, and there we get it, right? So this gives us a new copy of the list, which result now is. And so now I can append to result. I can return the result, right? The return value is the modified list. I go back to the main program. I printed out the result. And now when I print out original, right, original remains unchanged, unscathed. I was changing a copy and not the original. So the cost was I had to make a copy of my list. 4 items, no big deal. 40,000 items, maybe a big deal, right? I mean, maybe that's what I want to do, and I just have to pay to make the copy. But the reason why that doesn't happen automatically is that Guido says lists might be big, and I'm not going to make you make a copy every time. Okay, so comments or questions about this? Okay, let's keep going. So we saw what happened when we create a new copy that way. Let's do another thing. Let's say L.extend. So the append method takes an item and sticks an item into the list as the last element, right? So it tacks the item onto the end. Extend takes two lists, a first list and a second list, and joins them together, right? So the difference between append and extend, right? Sometimes you want one, sometimes you want the other. The difference between append and extend is that append takes a list and an item. Extend takes a list and another list, and both of them return, assuming that the item and the list contains what the item was, they return the same thing. So L.extend, a list containing I, right? Extend takes a list and another list, and it's going to join those two lists together, but it's going to have the same result. Extend works the same way as append does. And so we can run this, and it works, except that it's a different function, different method. It works the same way. There we go. We just did L.extend, and there's the 999 at the end of the same plot of land that we called it with, because we're passing by reference. We have a reference to the original memory, no copy necessary. So we return. Okay, so I need, of course, to, actually I don't need to do that at all. What I could do is just return L. So let me just, to preserve the example, let me put that return statement here. But here, I don't need the result. I'm just extending L. I can return L. And just to run through it again, click, 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 click. Right? By reference, do the extend. Whoops, there it is. Return that. So we get, there's the return value, but it also changed the original. And there we have the original. Okay, so this one had a side effect, which is what we expected. Let's do a different version. Well, extend and append both join things together, right? Append takes a list and an item. Extend takes a list and another list, and they're joined. So with extend, you can have the second list could have more than one thing in it, right? Append, the second argument is a single value. Okay? But they both create a larger list from two smaller lists. Okay, so now let's do this. Check this out. Have our original list. We concatenate, we add another list to it. So this is doing what extend does, but it's doing it with the plus operator. And let's see what happens. Let's see what happens. You're probably not going to like it. All right, start off all the same. We call the function. So we have our link back to the original. And we have our parameter 999. So here, L gets L plus the list containing the second parameter. The assignment statement creates a new copy. So we got a new copy. We can back up. The assignment statement creates a new copy. That's interesting, actually. All right. All right, so the assignment statement this gives us a new list, a new value. Here it is. And we assign the reference to that to L. So L no longer points to what it pointed to before because we reassigned it. And what we reassigned it to was a new list created by the original list sticking I onto the end. This by itself here, highlighted, this doesn't say anything about changing L, right? The blue part, the highlighted part, doesn't change L. That expression to the right of the equal sign creates its own list. So we have the yellow, the second yellow list with the 999 at the end. That's what the blue part gives us. And then we just take the reference to that list and stick it into L as the parameter of the function. And that's what breaks the link back to the original and creates the copy. So this one has no side effect. No. Did I actually show that finishing running? Just run this through again. Boom, 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 boom. There's the copy, and we return the value and print that out, but the original is unchanged, okay? Because the assignment statement here made a copy. You don't like remembering these rules, right? If you don't like remembering these rules, don't change the parameter in your function, right? Now, that'll cost you sometimes making a copy. So, when push comes to shove and you write programs that deal with real life-size chunks of data, you might have to revisit that decision to make your program, take less memory and run faster. But for our purposes, for correctness purposes, right, if you always make a copy, if you never assign to the parameter of the function, right, have a separate variable in the function called result, build that result, return that result. If you never assign to L, you never potentially change things with a side effect back in the main program, and you never have to worry. That's a style of programming called functional programming that you'll revisit in a couple of quarters maybe. But if you want the sort of simple rule not to have to furrow your brow with these kinds of concerns, the rule is don't assign to the parameter. Don't change the parameter, right? All these things with side effects, you get by changing the parameter, and the ones where you just take the original, don't change it, assign it to something else, you always get a copy. Okay, so this one gives you a copy too. That's why why it's nice to just have a rule of thumb. If you don't do this and do it some other way, you're better off. Okay, so comments or questions? Yes, go ahead. You should try to avoid side effects. Side effects are bad. I'm sorry? Because it makes your program unpredictable, or more unpredictable. It makes it harder to find the bugs, harder to change the things. It has, if your program interacts, or if your function, let's say, interacts with the rest of the program in one prescribed way, that is, it takes some arguments and it returns a return value, that's easier to follow than if it takes some arguments, maybe it returns a return value, maybe it changes other things elsewhere in memory. All of a sudden, there's a whole lot more stuff you've got to think about, right? And, there are lots of programs written that way, but, they tend to have more bugs than the programs that are written in the functional style where it's all done by passing stuff back out of the function by the return value. No, unless there's some other thing linking to it. So, if we have that original list and we change it, then what we unlink. Let me just have a picture here. Okay. So if I were to say, forget about the function, right? If I were just to say original gets the list 1, 2, 3. I have new memory here with the list 1, 2, 3, and this wouldn't have anything linking to it anymore, which would cast it adrift in space And Python sweeps up all the junk that's left in space and collects it. It's called, get this, real, not made up. That's called garbage collection. Right? In the running of a program, from time to time, there are parts of memory that aren't used anymore. And there's no way to get to it. There are no links to it. And the technical term for that is garbage. And there are algorithms for doing garbage collection, of identifying that unused memory and recycling it. And so that's what happens in Python. There's some programming languages where you have to do your own cleanup, and the garbage collection doesn't happen for you, but in Python it does. Okay? So yes, if we just change that value so there's no more links to the list containing 23, 45, 67, 89, that just disappears, gets recycled. Right? The memory can be used for something else later in the program. Okay? All right. Other. Yeah. Could I do a, sorry? Yes. Let me with the lists, and then we'll try and do something with name tuples. That'd be fine. Other things so far. All right, let me do one more list version. If you didn't like the last one, you're really not going to like this one. I'm sorry, I didn't make it up. It's just how it works. But you probably know this shorthand, right? So this shorthand, doesn't have to be with lists, right? We can say x gets x plus 1, and okay, so let me take this, put it on its own line, just so that we know. But I don't know if I said this explicitly. I'm sure you've seen it in the book. Turns out statements of this form are very common in programs. Take some value and increase it by 1. They're so common that the designers of C in 1972 said, let's have a special assignment operator that captures this pattern. So you can say in Python as well as in C as well as in Java, x plus equals 1, which has the same effect as x gets x plus 1. Right? So take the value, increase it by 1, store it back in the same place. That's what we're talking about here. Okay? So it's a shorthand, and most people, at least when they start out, think of it just as being a shorthand, save you a little bit of typing. But there's actually an underlying difference in how it works. The underlying difference in how it works is that we don't make another copy of x. Now, it doesn't matter if x is just a number. It does matter if x is a list, right? Because here we already saw with L on the right-hand side, we made a copy of the list. Here, there is no L on the right-hand side. So even though we think that the effect of this is going to be the same, this is going to change the original L. This is going to give us a side effect. Oops. Okay, so watch what happens. There we go, there we go, there we go. Here we are in the function. We start out with L pointing to that, and now we say L plus becomes I. Boom, because we're just referring to the same original L, no L on the right-hand side, no copy, and we're going to return L, and it will have changed, right? So here's the return value, but the original is also changed because we were referring to the same real estate, the same stuff in memory inside the function. All right, so plus equals is not the same as L gets L plus 1 or L plus whatever. That gives you a side effect. The other one doesn't because there's a copy is made because we create a new list on the right-hand side of the equal sign before we go back and reassign it. And that new list doesn't get created in the last example. Okay, that's what's happening. If you aspire to be a heavy-duty programmer, eventually you're going to have to kind of realize how these things work. If you want the quick rule of thumb before you get to the point of having to worry yourself about that, the quick rule of thumb is don't assign to the parameter. If you don't assign to the parameter, then it's very clear where you're making a copy and where you're not. But if you assign to the parameter, sometimes it changes, sometimes it doesn't. There are reasons for what happens when, but it's all kind of arcane and not necessarily something you want to be worrying about at this point in your career. All right. Comments or questions about this? Yes. Yeah, I mean, was it a statement like, whoops, was it a statement like this in the loop, or similar but maybe not exactly this? All right. Well, so if you were assigning back to the original list, it's hard to know. Something funny could have happened. You have to look at the actual code, but this is true. It's a slightly radical thing to say, given the way most people write programs most of the time. But assignment statements are dangerous. Right? Assignment statements are dangerous because you're plugging a value into memory. And the more you do that, the harder it is to keep track of what's going on. Now, an assignment statement to a constant that you never change, right? Tax rate equals 0.08, no big deal. But when you're changing data with an assignment statement, unpredictable things can happen, as we see here. Now, that doesn't mean you don't have to use them, but you have to be a little bit careful. And there are styles of programming where you just don't have assignment statements. Right? You do everything by calling functions and returning values from functions. And that's called functional programming, and it's less error prone. It's not something most people practice, but it's there, and you heard it here first. More and more, for a variety of reasons that sadly we can't talk about, but more and more people are going to be doing functional programming. Okay, other comments or questions so far? Yes? Generally don't. I mean, I don't think that's an absolute promise that every method changes the original and every function doesn't. I mean, I just wrote a function here that's a function and not a method, and depending on what I put inside it, it can change the original. So it's not an absolute rule, but it's certainly true with sort and sorted, and it's certainly true that append and extend do change the original. But there's not a simple rule that you can always count on, unfortunately. That's exactly right. That's exactly right. So there's no named tuple thing dot extend. Right? Extend changes the original. You can't change the original of a named tuple or of a string because they're immutable. And so you're exactly right. Yeah. Other comments or questions so far? Yes?
When we're implementing a function, is it always better to end with return rather than print so that we can do it?
Yes. Right. I mean, if the problem says write a function that takes some whatever and prints out, then your function should say print. If the specification doesn't say write a function that does whatever and prints out, if it doesn't say print it out, then return the value and don't print it out. I mean, that's just generally the best advice. Because if you just return the value, whoever calls the function can decide what to do with it. They're not stuck with the answer being on the console. They just have the answer. And they can stick it into a list, or they can print it, or they can send it across the network, or they can draw it on the screen, or they can do whatever. It's just much more flexible. And you can write assert statements to test it, right, which you can't do with print statements in the function very well. Other things so far? Okay, let me show you one or two other little things. Let me first copy this code. And now let me just do this. And let me do this with a string which is immutable. And I want to say here, right, so this is all going to be the same, but let me so this is what's going to be different. This formulation changed the original with a list because lists were mutable, but strings are immutable. We always make a copy. Okay, so that should do. Let's see what happens. And that stays the same. There's Donald Duck. We call the function. We print out the Donald Duck. We call the function add to end, right? And look, before I do that, here's the copy, right? The parameter was copied, right? We don't have an arrow here that goes back to this Donald Duck. We just have another copy of the Donald Duck because strings are immutable, which means copies are all automatically passed. We don't make the link back. So given that we have that, we can say s plus becomes x, and why doesn't this work? I can't. Anybody see what I did here? Say it again. Line 6, S. Oh, of course. Duh. All right. This is a list. I don't want the list, right? I tried to. I got to edit the code. I tried to convert my list example to a string example and fixed everything except this. So now we're okay. Thank you very much. Make the copy. S becomes equals I. Stick item I, which is a capital X, on the end. The return value is that. We get that. And it didn't change the original because we made a copy in the first place automatically because the string was immutable. Right? So there's the string example. Comments or questions about that? Okay. So there's a question about doing it with a name tuple. A name tuple would behave the same way as the string behaves, right? Because name tuples are also immutable. So when we pass the name tuple in, we would make a copy of that, and any changes would be made to the copy. Okay, comments or questions about that so far? Let me just say one other thing or two. Yeah, go ahead. Yeah, so right. So if I want to change If I want this variable in my outside program to change, I can assign to it, right? Okay, so here in the main program, I can reassign name to some new value. That's okay. But I've got to do that in the main program. I can't reach back from the function to change the argument, which I do get with a list. Okay, let me just say one other thing, kind of prime your minds for next week's lab if you get a head start on that. We have a restaurant name tuple that we've been looking at, right, that has a name field and a cuisine field and a telephone number field and a string field that's the name of the best dish and a number that's the price of that dish, right? So we've seen that a bunch of times already, working with it in the lab this week. Imagine that we had instead, let me just move back here. Okay, so imagine that a dish has a name and a price and a number of calories, right? And that's its own name tuple. But imagine we have a list of those, right? Because a typical restaurant serves a lot of dishes, not a single best dish the way we've done up to date. But imagine that we have a list of these dish objects with all the things that are stored, that are served by the restaurant, each of which has a name and a price and a number of calories. And that list can be the last field of the restaurant. So the restaurant still has a name, its own restaurant name, still has the cuisine, still has a phone number, and then it has a menu, which is a list of these dish objects. That's what's going to be in next week's lab, one of the things. And you can keep building up from there, but the idea is you can have name tuples that include lists, and you can have lists that include name tuples. We've seen lists of restaurants and lists of students and lists of books and lists of that. But a name tuple can have its own list, and if you have a list of restaurants, then each restaurant has its own menu, and you can go through every restaurant and look at all the menus and find all the restaurants that serve a particular kind of dish, or that serve dishes that are below 500 calories or whatever it is. So that's just to plant in your minds at the moment. Other comments or questions at this juncture? All right, thank you very much. Have a lovely weekend. Happy Halloween. I'll see you on Tuesday.
So you mentioned that lists data exists on the heap.
Yes.
So if my intuition is correct, then when Python declares a list, it's basically creating a pointer to an array of values on the heap.
Well, it may not be an array of values, but it is a collection of values.
Okay.
Yeah, I mean, arrays are always stored sequentially, and exactly right. And lists probably aren't most of the time.
Okay.
Yeah.
So okay.
Good. Hey.
Seems a string is immutable, but how does the replace method work?
The replace method makes a copy.
Makes a copy. Okay, thank you.
You're already tired? Ah, come on.